Hello everyone, my name is Sohan Patil and our team name is Lexicon. We are presenting the paper with title Scaling Data Constrained Language Models. The paper was published by Niklas Meningoff and other scholars. These scholars have pulled their expertise to address one of the most compelling challenges in AI, that is, how to scale language models effectively and responsibly. The discussion of this paper will be in two parts. First, we will see scaling language models and ask questions like what, why, and how. In the second part, we will see the components of this work that will work on problem on scaling laws under data constraints. In this research, we are focusing on three main aspects of language models: the model size, the training data, and the training compute. First, the model size. This is like the brain of the model, with parameters being the individual parts of the brain. Think of each parameters as a tiny piece of knowledge the model uses to understand and generate language. Second, the training data. Imagine this as the model's education. It's made up of tokens, which are pieces of text that the model learns from. More tokens means more information for the model to learn. Third, the training compute. This is the amount of math the computer needs to do to train the model. We measure this in flops, which stands for floating point operations, or the number of calculations it makes. These parts are interconnected. The bigger the model and the more it learns from data, the more computing power it needs. To give you an idea of scale, an early model like BERT started with about 109 million parameters and learned from 250 billion tokens, requiring a significant amount of computer calculations. GPT-3, a much bigger model, has 175 billion parameters and learned from about 300 billion tokens. Then there's Palm, which is even larger, with 540 billion parameters and 780 billion tokens of training data. As these models have grown, companies have become more secretive about the exact details. But the trend is clear. Models are getting bigger, requiring more data and more computing power to train them. When someone in charge, like a company executive, is deciding on how to teach a language model, there are two important questions they need to think about. First, return. This is like asking if we make the model bigger or give it more information to learn from, how much better will it perform? It's about understanding the benefits we get from improving different parts of the model. Second, allocation. This means figuring out the best way to use our resources. It's about deciding how to balance the size of the model, the amount of information it learns from, and the computing power needed. It helps in choosing the right combination to train the model effectively. These questions help determine the most effective way to create a model that's both large enough and smart enough without wasting resources. When discussing how improvements in language model performance can be quantified, research from OpenAI in 2020 provides significant insights. This research indicates a predictable pattern of performance enhancement when we scale up the model size, the data it learns from, or the computing power utilized. To visualize this, imagine a graph with both axes on a logarithmic scale. On such a graph, each axis increment represents a tenfold increase. The resulting line on this graph would clearly illustrate a steady decrease in the model's error rate as we increase the model size, augment the data volume, or enhance computing resources. For instance, multiplying the data input by 10 typically results in a notable reduction in error rate. These graphical representations are invaluable for justifying substantial investments in computing power to advance the capabilities of these models. The question of how to best use our resources when creating a big language model is really important. It's about figuring out beforehand how many parts of the brain, that is parameters, the model should have in relation to how much it learns, that are training tokens. In 2022, a study known as Chinchilla did a bunch of experiments to find out the best way to use a set amount of computing resources. They wanted to see whether it's better to have a bigger brain, that is more parameters, or more learning material, which means more tokens. They looked at four big language models and noticed that past models might have had too many parameters and not enough data to learn from. For a model to be compute optimal, meaning it uses its computing power in the smartest way to get better at its task. The study suggests that the number of parameters and the amount of data should be balanced. They think that if we keep this balance as we are able to use more computing power, we will continue to make the best possible models without wasting any computing effort. The Chinchilla study is key for anyone interested in how big language models are trained. In the paper, they present an easy to understand formula to guess how well a model will work. This formula looks at two things: the size of the model, that is how complex it is, and the training data, that is how much it gets to learn from. In the formula, n stands for the number of parameters, like the number of different concepts the model can understand. D is the number of tokens, basically the chunks of learning model. The formula breaks down the expected quality of the model into three parts. The first part guesses how close the model can get to the ideal way of generating language. The second part takes into account the amount of data the model has seen, acknowledging that seeing more could probably help it improve. The third part is about the lowest error rate the model could possibly reach, which is tied to the complexity of the language itself. The letters A, B, E, alpha, and beta in the formula are values that come from a bunch of tests and experiments. The important finding from the chinchilla is that the values for alpha and beta are about the same, which supports their suggestion to balance the number of parameters with the amount of training data. Formula from the chinchilla paper suggests that as computers become more powerful, we are going to want to build even better language models. These advanced models are going to need a ton of data to learn from. Researchers think we might soon run out of enough high quality data or tokens for these hungry models. A graph they have shared suggests we are getting close to using up all the available data we have as we aren't creating new data quickly enough. Even though there's some uncertainty in this prediction, it seems likely that in the next few years we will use up the good data we currently have access to. When we look at really good quality resources of data like academic papers or books, there's a lot, but not endless amounts. About 1 trillion tokens from papers and 1.6 trillion from books. Sources like Wikipedia have more to give but are quite small compared to the need. When we include coding data from places like GitHub, it gives us a lot more, about 14 trillion tokens, which could help with the shortage for a while. But the situation is more urgent for languages spoken by fewer people. For example, for Finnish, which has about 6 million speakers, there's only about 38 billion.
When they created GPT-3, they tried not to use the same data more than once during training, only making a few exceptions like Wikipedia. The creators of the model called Palm did something similar. They used each piece of data only once when training different versions of the model, being careful not to duplicate data. It seems that the common rule when teaching these big models is not to go over the same data multiple times. The question the researchers are asking is, why is reusing data not a good idea? They are curious about the reasons behind this practice and if there's a way to improve how we use the limited data we have. In this project, a practical hands-on approach is used. With the help of a powerful supercomputer cluster, around 300 experiments with a large language model of moderate-sized data were conducted. Three different versions of the model are focused. The first version has 2.8 billion parameters, the second has a 4.2 billion parameters, and the third has 8.7 billion parameters. For each of these models, a specific amount of unique data tokens for training were used. All the models were trained using a method similar to GPT-2, a type of artificial intelligence model known as a transformer. To explore how using the same data more than once affects the model, the data is split into smaller parts. Model was trained 8 times, each time varying the amount of data being repeated. To keep it straightforward, the term epoch is used to describe how the models are trained with the data. One epoch means the model goes through the data once. When we say two epochs, it means the model is trained through the data twice, which is like using half as much unique data because we are repeating the data that's already used. In this experiment, the model is trained using the data just once, which we call one epoch. Here, a typical decrease in error was observed, known as a loss curve, which was consistent across all three model sizes. After training for two epochs, the loss curve was very similar to the first, with only a minor difference noticeable towards the end of the training. As the epochs were increased to 4, only using 25% of the original unique data, surprisingly, the loss was almost the same as when using more unique data, showing that repeatedly data didn't initially hurt performance much. However, the situation changed when used the data more excessively. At 14 epochs, there was a significant increase in errors, indicating poor model performance. And by the time of 44 epochs, the results were very poor. The experiments show that repeatedly using the same data diminishes its value significantly over time, especially after many repetitions, leading to worse performance in our models. We think this decrease in value can be described similarly to how radioactive substances decay over time. Each time we use a data point, it loses a bit of its initial usefulness. like how radioactive materials lose their potency after half-life. As we continue to use the same data again and again, its usefulness or value drops sharply. Since using data consumes computing resources, the value of the data eventually becomes almost negligible as it used repeatedly. In the graph setup, 100% means one epoch and 25% represents four epochs. All these points use the same amount of computing power. In the graph, the dotted line shows what the loss would look like if there was no decrease in value from repeating the data. That's delta equals to 1. The dashed line shows what would happen if repeating data added no value at all. That's delta 0. The yellow line shows the actual predictions from our model, which calculates loss based on how much data's value decreases with each repeat. This experiment is done in three different scales, each time with a bigger model and more unique data. The results consistently showed that as we repeat data more, the effectiveness of each repeated data decreases, affecting the model's performance.